Okay, so discovered the electron. That led to a lot more questions. So if there are negative charges, there must be some positive charges, because we knew that atoms, that matter in general, did not have a charge on it. And so then how are these particles arranged? Are atoms just some sort of jumble of even more fundamental particles? There must be a positive charge. We know there's a negative charge. How many other particles are in there? Are those individual particles solid spheres? Are they layers, or what do they look like? Is there some structure to them on the inside? Tons and tons and tons of questions. So Thomson came up with what's called the plum pudding model. Anybody ever had plum pudding? This is not an American thing. This is a British thing, right? The British use the word pudding in an entirely different way than we do, right? Okay, so when you see plum pudding, think blueberry muffin, okay? It's not a blueberry muffin, but that's the closest thing we have. Y'all at least seen a blueberry muffin, right? Okay, good. So you've got this muffin, like cake, right? And then there's blueberries in it, and they're just kind of random, right? And sometimes they end up being together, but usually they're kind of spread out. So this was his starting idea of this is what's going on. The electrons were the blueberries in the muffin, and then there's some sphere of positive charge that is the muffin part. Okay, so you can't investigate this without having a hypothesis to test. So this was his hypothesis, his model of the atom. So before we can talk about why that wasn't correct, we have to talk just a tiny bit about radioactivity, which gets covered more in chapter 21. I think that number is correct. Anyway, what's radioactivity? It's evil, it's bad. No. It's the emission of small energetic particles from the core of certain unstable nuclei. Radioactivity is natural. This isn't something we've done to the environment. Radioactivity is natural. It was discovered at the end of the 19th century. And this discovery allowed scientists to probe the structure of the atom. So there are three main types of radiation: alpha particles, beta particles, and gamma rays. And so the only one we need to know about right now are these alpha particles. Alpha particles have positive charges, and they are the largest of the radioactive particles. So Rutherford had worked with Thomson, and he set about to do an experiment. He was not trying to disprove his boss's hypothesis or theory. He was trying to confirm it. So in this experiment, he directed positive alpha particles at an extremely thin sheet of gold foil. So in the plum pudding model, where you've got mass and charge spread throughout the entire volume of the atom, the prediction was that these particles would just go straight through. Just go straight through there. Here's an illustration of the setup here. So here we have a source of alpha particles. Again, these are positively charged particles, very small. Shooting them at this gold foil. We've got this detector in a ring around this so that we can see where those particles go, because you can't see them, but you can see them hit the detector. And here's the gold foil. The results were that most of the particles went straight through, which is what he expected. Some of them were deflected a bit, but some of them essentially bounced back. He did not anticipate that. That was shocking, actually. Approximately 1 in 20,000 of those particles bounced back. And he said this is about as credible as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you. A 15-inch shell, that's like a 15-inch cannonball fired at a piece of tissue paper. Is that going to bounce back and hit you in the face? Of course not. It's going to go straight through. No, but 1 in 20,000 times it bounced back. Crazy, right? So this doesn't fit with the plum pudding model of the atom. So we got to come up with something else. So Rutherford created a new model. His conclusion was that matter must not be as uniform as it appears. There must be regions that are basically empty, and then small regions that are extremely dense. And it's these extremely dense regions that are causing those particles to bounce back. So the predicted result, based on the plum pudding model, was that the particles would just go straight through. The actual result is that a lot of them went straight through, most of them, but some of them bounced back. So the nuclear model says that the nucleus is this region of positive charge and extreme density, and if those alpha particles hit the nucleus, they'll bounce back. So if we change our analogy from shooting cannonballs at tissue paper to shooting maybe airsoft pellets at a volleyball net, most of the airsoft pellets are going to go through the big holes in the net, right? But what if the pellet hits one of the strings straight on? It's not powerful enough to go through the string, so it's going to bounce back. So that's kind of the idea here. So building on that idea, Rutherford proposed the nuclear theory of the atom. 3 basic ideas. Most of the atom's mass and all of its positive charge are contained in a small core called a nucleus. Most of the volume of the atom is empty space, throughout which tiny negatively charged electrons are dispersed. And there are as many negatively charged electrons inside the nucleus as there are positively charged particles. The electrons outside the nucleus as positively charged particles within the nucleus, so the atom is electrically neutral. Those positively charged particles are called protons. So positive starts with a P and proton starts with a P. This model was very successful. People had a hard time, finding anything wrong with it. But it wasn't quite complete, because one thing that didn't work out was hydrogen has 1 proton and helium has 2 protons. So you would expect that a helium atom would weigh twice as much as a hydrogen atom. But the mass of helium is actually 4 times the mass of hydrogen. So something was missing. So Rutherford was also involved in this, and one of his students, James Chadwick, demonstrated that this unaccounted for mass was due to neutrons. So neutral particles within the nucleus. So neutron, neutral, you get the idea. So neutrons have no electrical charge. So, as we're constructing this atom in our minds, we've got the protons in the nucleus and we've got electrons just kind of floating around here. We'll learn way more about that than you want to later. And then there's got to be something else in there that would account for this extra mass in helium atom, and that's the neutron. So the neutron has a similar size, a similar mass to the proton, but it doesn't have a charge. So now we can fix our theory so that it fits with the relative masses of hydrogen and helium. The hydrogen atom has 1 proton and no neutrons. In a helium atom, we've got 2 neutrons and 2 protons, so 4 of these massive particles, and that's why the helium atom weighs 4 times as much. So the nucleus is extremely dense, and that's an understatement. It contains over 99.9% of the mass of the atom, but occupies very little space. So, a couple of things to help us understand this. The cloud analogy. So, electrons, we could think of them as being like water droplets in a cloud. Or fog, right? We all know what fog is like here in the valley. So you think about a really good foggy day when school's delayed by a couple hours. We don't get foggy days in college. Sorry. We have to just risk our lives. Anyway, you know what fog is, right? So you can see the fog, right? And it's difficult to see through the fog because it blocks light. But you can also walk through the fog, right? It's mostly empty space, right? But little tiny particles of water suspended in the air. Teeny, teeny, tiny particles. Those are like the electrons. The fog occupies a large volume, but if you were to condense, to put all the water together, it would not amount to very much at all. And yet it takes up a lot of space. It's mostly empty space, the fog is. It's not dangerous because you run into the fog. It's dangerous because you run into the other objects that are in the fog that you can't see because of the fog. So matter is much less uniform than it appears. I mean, look at this, the bench that you're sitting at, right? It's shiny for the most part, and black, and looks pretty smooth. There's a little bit of variation, but it looks pretty smooth, right? It doesn't look like it's made up of Lego blocks. Any of you guys been to Legoland? Down in Southern California? It's pretty cool. They have some really, really big Lego structures. They have the Taj Mahal made out of Legos. They have Mount Rushmore made out of Legos. You know, it's like, I don't know, 10, 15 feet tall. It's really big, but much, much smaller than the real thing. Lego bricks have those little knobs on the top so they stick together, and they're square, right? So if you build something that's curved out of square blocks, when you get far, far away from it, it kind of gets fuzzy and it smooths, right? But then when you zoom in, you see it's all these little pixels. It's kind of like a Minecraft thing, right? Everything is blocks. So with matter, the thing is that the differences in the particles, the density, is so small that we can't detect it. So again, some size comparisons. If the nucleus of an atom was the size of a period, like on the printed page, the electrons would be 10 meters away. Okay, that's 10 of these sticks, 10 yards. A period is the nucleus, and then 10 meters away are the electrons. And what's in between? Nothing. Empty space. And that's an atom. It's mostly empty space. If you took a grain of sand, and instead of being composed of regular atoms, it was composed of just the nuclei squished together to make that size, it would weigh 11 million pounds. Grain of sand. 11 million pounds. And yet a grain of sand weighs a fraction of a pound, right? Because it's mostly empty space. Think of some scaffolding or a jungle gym, the old-fashioned metal kind, right? Composed of a bunch of bars, but mostly empty space, right? So here we're going to imagine scaffolding that's the size of a football field. So 100 yards long, about 100 meters long, and 100 stories high. That's a big jungle gym, right? My son Andrew would have so much fun on that. But it'd be kind of scary when you climbed up too high, right? Mostly empty space. And yet if you looked at that from outer space, that would be big enough that you could see it, right? From a satellite. It's not going to look like it's mostly empty space, right? It's going to look solid. And here, just with this image, you can see that as you get far away from it, here for scale is this little man down here. You can see that because you're seeing further in and seeing all these bars, even though it's mostly empty space, as you back up from it, it begins to look like it's solid. In that structure, if that were an atom, the nucleus would be the size of a green pea in the middle, with a few electrons floating around. So when you wrap your knuckles on the bench top, what you're doing essentially is you're taking the scaffolding in your knuckles, which is mostly empty space, and you're banging it against the scaffolding in the bench top. They are both mostly empty space, but they don't fall into each other when they contact. Matter appears solid because the variation in density is too small for our eyes to detect it. So from this distance, it's being so small that it looks solid. Does anybody have any questions about that? I've never thought about matter that way before. It's a little disturbing. Kind of makes you think about science fiction in any way too, because when in the old Star Trek movies, the transporters where they beam you up, and they take your particles and they just transport them. Well, is that so far-fetched? Maybe not. Maybe that could happen, right? Maybe you could make something that could travel through a solid wall, because matter is mostly empty space. Gives you a lot of ideas.